Welcome to a deep dive into the holographic universe.
Exciting stuff.
Yeah, you're curious about the idea that our universe might be like a hologram, and you've provided a fantastic article summarizing some key physics papers about black holes and the holographic
With
principle.
a lot to unpack there.
It is a lot.
Yeah,
This article is dense. It covers decades of research, but we've distilled it down to the most fascinating and important nuggets for you.
I think they'll be pleased.
Get this. Imagine everything we experience in 3D being a projection from a 2D surface. It's a wild idea.
Right. It's a concept that really challenges our understanding of reality.
Absolutely. But to grasp this mind-bending concept, we need to start with something a little more familiar. Black holes. They're not just empty space as some might think,
Yeah.
but regions where gravity is so strong that nothing, not even light, can escape.
Exactly. And for a long time, black holes were thought to be incredibly simple, defined only by their mass charge and angular momentum. But this view changed dramatically in 1973 with a groundbreaking paper by Jacob Bekenstein. He proposed that black holes have something called entropy.
Okay, entropy. For those of us who aren't physicists, can you break down what entropy is?
So think of entropy as a measure of disorder or the amount of information packed into a system. What made Bekenstein's idea so revolutionary is that it implied black holes weren't just empty voids, but complex systems with their own internal states.
So black holes hold information. That's a pretty big deal.
Right.
But here's where it gets really strange, right? The article mentions that Bekenstein's work showed a black hole's entropy is proportional to its surface area and not its volume. How does that even make sense?
It's a key insight that hints at something profound about information and space. Imagine you have a box full of gas. You would naturally assume the entropy, the amount of disorder, is linked to the volume of the box, right? But with black holes, it's all about the event horizon, that point of no return. The amount of information a black hole can hold seems tied to the area of this boundary, not the volume inside.
So the event horizon, the boundary beyond which nothing escapes, is the key.
Exactly. And this surface area relationship really shook things up in the physics world. It paved the way for Stephen Hawking's incredible discovery just a year later.
Hold on, you're talking about Hawking radiation, right? Black holes aren't completely black after all. They actually emit particles due to quantum effects near the event horizon.
Precisely. And it's not just random radiation, it has a thermal spectrum, meaning black holes have a temperature. This was a major breakthrough because it connected three fundamental areas of physics: quantum mechanics, general relativity, and thermodynamics.
Okay, so we've got black holes with entropy, they radiate energy, and they have a temperature. This is definitely pushing my brain to its limits. And speaking of limits, the article mentioned something called the information paradox. What's that all about?
That's where things get really tricky. Quantum mechanics, the theory governing the subatomic world, states that information can never be truly destroyed. But if black holes eventually evaporate due to Hawking radiation, what happens to the information about everything that fell into them?
So does that information just disappear? Wouldn't that break the laws of physics as we understand them?
That's the paradox. It seems like information might be lost, which contradicts quantum mechanics. This has puzzled physicists for decades and has been a driving force in searching for a theory that unites general relativity and quantum mechanics, a theory of quantum gravity.
So black holes are basically throwing a wrench into our understanding of the universe.
You could say that they force us to re-examine some of our most fundamental assumptions about how reality works. And this is where the idea of the holographic principle starts to emerge.
Okay, I'm ready to hear more about that, but can we take a quick pause to let all of this sink in first? Black holes are stranger than I ever imagined.
Take your time. The journey into the holographic universe is just beginning.
Okay, I think I'm ready to jump back in. We've established that black holes are far more complex than we initially thought, and they're really shaking up our understanding of information and reality. So where do we go from here?
Well, these mind-boggling discoveries about black holes, particularly the information paradox and the strange connection between entropy and surface area, led physicists to some radical new ideas. One of the key figures in this story is Gerard Hooft, a Dutch physicist. Back in 1993, he proposed that all the information contained within a 3D volume could actually be encoded on its 2D boundary.
Hold on. Are you saying that everything inside a 3D space like this room we're in could be described by information on a 2D surface, like the walls, ceiling, and floor?
Yeah, that's the basic idea. It sounds crazy, but remember what we discussed about black holes. Their entropy, their information content, is related to the area of their event horizon, not the volume inside. Hooft took this concept and suggested it might apply to more than just black holes.
So it's like the information about the entire universe could be stored on some kind of cosmic boundary.
That's one way to think about it. This concept is a cornerstone of what we now call the holographic principle.
Okay, so we've got black holes behaving strangely entropy-linked surface area, and this idea that 3D information could be encoded on a 2D surface. This all leads to the holographic universe.
You got it. In 1995, Leonard Susskind, an American physicist and one of the pioneers of string theory, took the holographic principle to its most extreme conclusion. He proposed that our entire 3D universe might actually be a projection of information encoded on a distant 2D surface.
Wow, so we're like characters in a video game living in a simulated reality.
Not exactly. It's not about a computer simulation in the traditional sense. The idea is more that the information describing our universe, everything from the laws of physics to the position of every particle, might be contained on a distant boundary surface. And what we experience as our 3D reality is a projection of that information.
So if I'm picturing this correctly, it's like a shadow play.
Mm.
The shadow puppets create the illusion of a 3D world on a 2D screen, but the true reality is the movement of the puppets themselves.
That's a great analogy. It captures the essence of the holographic principle.
This is all incredibly mind-bending. Is there any actual evidence to support this idea, or is it just theoretical physicists letting their imaginations run wild?
While it's definitely a radical concept, there's actually a mathematical framework in string theory that provides some support for the holographic principle. It's called the AD-SCFT correspondence.
AD-SCFT. Could you break that down for me? I'm not sure I'm fluent in string theory jargon.
It's a complex idea, but the basic gist is this. It shows how a theory with gravity in a higher dimension can be perfectly described by a simpler theory without gravity on a lower dimension. This duality suggests that information in a higher dimensional space can be encoded on its lower dimensional boundary, just like the holographic principle proposes.
So this crazy math is saying that maybe our 3D world is like a shadow puppet show with a deeper reality playing out on a 2D screen we can't directly see.
You're getting it. And the implications of this are huge. It means that our understanding of space and dimension might be completely wrong.
So to recap, we started with black holes, which led to the information paradox and the idea that entropy is related to surface area. Then we have Hooft, suggesting that 3D information could be encoded on a 2D surface, followed by Susskind, proposing that our whole universe might be a holographic projection. And now we have this AD-SCFT correspondence and string theory that seems to support the whole idea.
That's a great summary. And it doesn't stop there.
Yeah.
Physicists are exploring all sorts of connections between entanglement quantum information and the structure of space-time itself.
Entanglement, that's when two particles are linked and whatever happens to one instantly affects the other, even if they're miles apart.
Yes, and it's turning out to be a much deeper and more fundamental concept than we originally thought. Some physicists believe that entanglement could be the key to understanding how information is encoded in space-time and how the holographic principle might work.
Wow. So even entanglement is connected to this whole holographic universe idea.
Yeah.
This just keeps getting wilder. But hold on. The article also mentions something called the firewall paradox. What is that all about?
The firewall paradox challenges some of our assumptions about what happens inside black holes. It suggests that an observer falling into a black hole might encounter a firewall of high-energy particles at the event horizon, contradicting the idea that crossing the event horizon should be a smooth experience.
So instead of smoothly falling into a black hole, you'd get incinerated at the edge. It's terrifying.
It's a thought-provoking concept, and it has huge implications for the black hole information paradox and our understanding of quantum mechanics.
It seems like the more we learn about black holes, the more questions we uncover. It's like peeling back the layers of an onion only to find more layers underneath.
Exactly. And as we delve deeper into these mysteries, we're forced to confront some of the most fundamental questions about the nature of reality itself.
It's both exhilarating and a little unsettling to realize how much we still don't know.
I agree. But that's what makes this exploration so compelling. It's a journey into the unknown, and with every step we take, we're expanding the boundaries of human understanding.
I'm ready for the next step then. If our universe might be a hologram, what does that even mean for us? What are the implications for our understanding of ourselves and our place in the cosmos?
Those are profound questions. And to be honest, I don't think anyone has definitive answers yet. But there are some intriguing ideas out there that I'd love to share with you.
I'm all ears. Lead the way. I'm ready for the next step then.
Yeah.
If our universe might be a hologram, what does that even mean for us? What are the implications for our understanding of ourselves and our place in the cosmos?
Well, some physicists believe that the information describing our universe might be stored on a cosmological horizon, a boundary at the edge of the observable universe. Others suggest that the information might be encoded in the fabric of space-time itself, woven into the very structure of reality.
So we're talking about some pretty radical outside-the-box thinking here.
Absolutely. And there's another mind-blowing idea that's been gaining traction, the idea that gravity itself might not be a fundamental force, but rather an emergent phenomenon.
Whoa, hold on a minute. Gravity emergent. You're saying it might not be one of the fundamental forces of nature?
That's what some physicists are proposing. There's been some fascinating work by physicists like Thanu Padmanabhan and Eric Verlinde suggesting that gravity could emerge from the thermodynamics of space-time or the entanglement of quantum information.
Okay, I need you to explain that a little more slowly.
Ah,
How can gravity, something we experience every day, not be a fundamental force?
think about it this way. Imagine you have a large number of gas molecules bouncing around randomly in a container. Individually, each molecule's motion seems random, but collectively they create pressure and temperature, which are emergent properties of the system as a whole.
Okay, I get that. But how does that relate to gravity?
Well, some physicists believe that gravity might work in a similar way. It might not be a fundamental force in itself, but rather an emergent property arising from the collective behavior of something more fundamental. Perhaps the microscopic degrees of freedom of space-time, or the entanglement of quantum information.
So gravity could be like the temperature of the universe, a macroscopic effect
Right.
arising from microscopic interactions.
Exactly. It's a radical idea, but it's gaining traction in the physics community. And if it's true, it could revolutionize our understanding of the universe and our place within it.
Okay, so we've gone from black holes to the information paradox, to the holographic principle, to the mind-blowing possibility that gravity itself might be an emergent phenomenon. I feel like we've taken a crash course in theoretical physics and stretched our brains to the limit.
It's been quite a journey, hasn't it? But that's the beauty of exploring these big questions. They force us to confront the limits of our understanding and to consider possibilities that might seem strange or even impossible at first.
Absolutely. And you know what? After diving deep into all of this research, I'm starting to see the world a little differently. I mean, if our universe really is a hologram, what does that mean for our perception of reality? What are the implications for our understanding of ourselves and our place in the cosmos?
Those are profound questions, and I don't think anyone has definitive answers yet. But that's what makes this whole area of research so exciting. It's pushing the boundaries of human knowledge and forcing us to reconsider what we thought we knew about the universe and our place within it.
Well, to wrap things up for our listener today, let's recap the key takeaways from our deep dive into the holographic universe. We started with the mind-boggling properties of black holes, their entropy, their Hawking radiation, and the information paradox they create. These discoveries led physicists to propose the holographic principle, which suggests that all the information about a 3D space could be encoded on its 2D boundary.
And we explored how this principle might apply to our entire universe, suggesting that our 3D reality could be a projection of information stored on a distant 2D surface. We even touched on the possibility that gravity itself might be an emergent phenomenon arising from the thermodynamics of space-time or the entanglement of quantum information.
It's been a wild ride, and I think the biggest takeaway for me is that we're still just scratching the surface of understanding the universe. There's so much more to discover, so many mysteries yet to be unraveled.
I completely agree, and I think the more we learn about the universe, the more we realize how much we don't know. But that's what makes it so fascinating. The pursuit of knowledge is a never-ending journey, and the holographic universe is just one of many exciting frontiers waiting to be explored.
Well, I think we've given our listener plenty to ponder today. If our universe is a hologram, what does that mean for our understanding of reality, free will, consciousness? These are big questions with, as you said, few answers. I have a feeling they'll be seeing the world in a whole new light after this deep dive. Thanks for joining us on this incredible journey.